Okay. Hi. Can you see my screen or not?
Can.
Can
Yes,
Okay.
teacher.
So thank you very much. Good evening, everybody. Everybody. So by right, we need to finish chapter one, and then we need to finish this chapter, heating and cooling for electrical machines. Um, so we are in week four lah. By right, we finish this one until the heating and cooling of electrical machine. I think we need to do the class replacement on this weekend or tomorrow. Later we discuss. So that we can cover all the topics according the teaching week lah. After that, yeah. Ni lab. Sorry tak start lagi. Sebab group dah siap lagi. We need to do the grouping first before the lab start. Jadi next week kita baru start lab lah. Last week kita sampai mana? Have a look. Where are we? Okay. Where are we now? Oh, okay. We are in here. Wow, a few lag behind. Okay, let me start. Can you get the answer or not? Hello, can you see my screen or not? Hey, hello. What? You type. Yes, sir. Okay. So, okay. So you can see my screen. If you type, saya kena dengar siap-siap. So can you get the answer or not? Ada buat atau tak ada? I don't know what to say. No response one. Astaghfirullah.
Tak buat sir, tak buat.
Hello. Tak buat
Ha.
Please go to do it Please go to do it, or else I cannot discuss one.
Okay.
So you need to do one. Slide ni saya ada bagi kat Google Classroom tak?
Ada.
Ada. Okay, can. So so the first thing is the same, magnetism. Okay, sorry saya punya itu drawing pad tak ada kat sini. So I need to use mouse. So last time I think you guys are very good in the electric circuit. Now what we can do is we want to learn about magnetic circuit. The circuit related to magnetic field. Circuit related to electric field, we call electric circuit. Circuit related to magnetic field, we call magnetic circuit. The main difference is material, and geometry, spatial. We call spatial. The property of space, S-P-A-S-E. Bukan special, not special. It's a spatial. The main difference is the material and spatial. You see this one? We are not seeing the 2D geometry or 3D geometry. No, we don't deal on that. But here we need to know the geometry. What is the length? Is it a circle, a solid, or rectangular? So that we know that where is the flux flow through the area, and then what is the material inside. So that's a difference. One is a spatial, like the area. One is a material, the mu. So this is the difference. But we want to make it simple. That's why we have a magnetic circuit. So usually when we come to the electric circuit, V equals to IR, right? Same as well here also, F equals to IR. Why we say so? Sorry, phi R. In magnetic, we have phi. Okay, in electric circuit, we have a voltage. Voltage, if you still remember, it is electromotive force. A force generated due to the movement of electron. This is the magnetomotive force. Okay, a force generated due to the movement of the magnetic field. Okay, So we want inside here. I think that time we talk about the formula code. Sini code is it? Maybe that day. I think that day. Do we talk about the formula? Do we discuss the formula before that day? Got right. This one. Okay. So in order to make the things easier, we try to map the last time the so-called you're very good in the electrical circuit to become a magnetic circuit. So we want to make it easier lah. So we have a V, we have I, we have R, then we have a analogously, analogously we have F, we have a phi, we have a reluctant. This is reluctant. I guess you are very good in during your 80-08 lah, nah? So and then we have what else? That's it lah. Go back and study, nah? So electric current flowing through. This one is a flux, not flow through. It is not actually flow through, but we call it as a flow in the sense. Nah? Then we have resistance. Here got reluctant. The flow of a current involves a continuous expenditure of energy. Energy is needed only for creating flux initially, but not for maintaining it. Nothing special. Just go on. This one I think we already discussed when we have a F equals to phi R. So what is F? F equals to the number of turns times the I. Then it will generate flux, which is a magnetic field strength and the length. The flux generated here will flow circular like this. So we represent like this. And then phi equals to BA. And B is what? B equals to mu H. Okay, mu is what? Mu equals to mu R, mu naught. R is what? R is a L over mu A. Mu is mu R, mu naught. So this is a different. It's not like V equals to I. Then V equals to what? Nothing. I equals to what? R equals to what? Nothing, right? But because we want to relate to the material, we also need to relate to the space. That's why we have such equation. So I put it in a simple way, which represent by this lah. Magnetic field, same area, flux. So what is that? This one actually we discussed about flux equals to BA lah. If you still remember this one, flux equals to BA, right? How we want to calculate flux? Plus, remember, the flux always taken as a perpendicular to the plane, crossing to this plane, 90 degrees. If let's say the plane is like this, okay? So the flux flow through, right? It is like this. Let's say lah, I mean flux. So we cannot directly use this value, saying that flux equals to BA. So B is calculated by use. Sorry, this is B. Flux is B times A. This one, let's say B is a 1 Tesla, A is a 10 meter. So 1 times A of 10 meter square become 10. This is not correct, because it is not 90 degrees. In fact, 90 degrees is like this. So this is not 90 degree. This is 90 degree. Then this B, let's say this is B2. Maybe it is not 1 Tesla, right? Because it got angle. So maybe we take 0.8 Tesla. So 0.8 Tesla times 10 meter square. Then we have 8 Weber. This one is correct. This one is wrong. This one is wrong. So I hope that you still remember during your second year PM learning. So permeability is the measure of ease with a magnetic flux line can establish in the material. So last time I explained in a way of keupayaan flux can flow through the material. Berapa tinggi keupayaannya? So if let's say the keupayaan is very big, then the permeability is very big. If let's say permeability is very low, which means when the flux want to flow through the material, it's very difficult. For example, maybe I draw here. For example, we have a B. of a 1 Tesla. If I measure here, the B is about 0.9 Tesla. Then this is the permeability is very good. If let's say I put 1 Tesla here, then we measure here, we have about 0.1 Tesla. Then this material is very bad because the flux cannot flow through. So this one must be memorized. Okay. Exam will not give you 4 pi 10 to the power minus 7. And then this one already no. And then this one you need to remember, usually non-ferromagnetic material, it is only one. For example, wood, glass. Okay. Yeah, we already talked about this one. Yes, reluctant. F equals to Ni, just now talk about it. I think this one we talked about it already by using the I want to go into here. Yeah, this one. So actually, for this few slide, I mean, until here, what we need to do is we draw out, put out like this. F equals to pi r. Remember when every time you want to solve this type of question, please write out this one first. F equals to phi r, then F equals to Ni equals to HL. Okay, phi equals to VA, B equals to mu H, mu equals to mu R times mu naught, R equals to L over mu A. That's it. That's it. Then Ampere's circuit law. Ampere's circuit law saying that the algebraic sum of the rise and drop of the NMF around a closed loop of a magnetic circuit is equal to 0, which means we want to principle conservation of energy if let's say we apply 2 Newton here, then we should receive 2 Newton another side. So same as well, this is a source of energy, Ni, which is HL, it convert into magnetic field. So the field will be absorbed by this material and also this material and this material. So 1, 2, 3. So which means the summation of all the MMF here will become the same as here. Okay. Now we know that MMF is what? MMF is F, right? F equals to phi r, which is MMF. Okay. Then MMF can be Ni, can be HL. So the thing is, Ni is here. It should be HL for everything. Every HL. So how many things we have? 1, 2, 3. Because there's a 3 material: iron, steel, cobalt. Different materials. So in our Ni should be HL plus HL plus HL, which is for material 1, material 2, material 3. So this one is for iron, this one for steel, this one for cobalt. It add up together should be same as the source of the energy. So if we can rewrite like this, so this one is steel, cobalt, iron. Boleh tak sampai sini?
Boleh.
Boleh.
Okay, thank you. Thank you very much. And then another one is the flux. Okay, this is a source of energy, and then flux will flow through, right? So flux also, analogous to the current. When it go through here, it will split into this and this. When it flow through inside here, it will join this and this. And then when they come up together, it become like this. So let's say flux A, it will split into flux B and C. Okay. Then flux B and C become flux A, like this. Okay. So air gap. Okay. When we talk about air gap, if let's say there's an ideal no fringing effect, okay, then there's no line here. Okay, what is fringing effect? The spreading of the flux line outside the common area. This is the common area. Okay, this would be the common area. If the line is flowing like this, then we will say spreading of the flux line outside the common area of the core. For the air gap then we call fringing. Okay, so the calculation will be different. So equivalent magnetic and electric circuit equivalently, we want to make it equivalently. So okay, source of energy and I lah, and then reluctance of the steel one material, then reluctance of the air another material. So usually we put C as a core, G as a gap lah. The flux is this one. So this is the equivalent circuit. So we apply the default direction. So plus, minus, plus, minus, plus, minus. So when the default direction go to negative first, so negative Ni, and then it go to the positive, plus V plus F phi R lah, phi RC, plus again phi RG. Okay, it become to 0 because no more nothing. Then we move this one to the other side, it become like this. Okay, so I hope that you still remember this circuit So I repeat again we need, before we want to solve this question, we need to draw the equivalent circuit. So this is the source of the energy. Usually we use plus minus. And then we know that we have a two material. One is a core, one is the air. So we will draw core, air. It is connected as series. So this is RC, this is RG. So flux current, flux will flow like this. Okay, for the source, always positive at the flux where it flow out. This is source. But when it is a load or material, when the flux go into it, it must be positive first, then negative. Then the flux, positive, negative. It must be like this. After that, we apply the default loop as a positive direction. So since the arrow is going to negative first, the negative and I. And then the flux go to the positive first, plus phi RC. And then go again, plus positive first, plus phi RG equals to nothing, no more, right? 0. So when we do some similar movement, then it becomes the equation like this. So a ferromagnetic core is shown in the figure. Three sides of the core are of a uniform width. A uniform width, which is the so-called width. How to determine uniform width? Width maksudnya ketebalan kot. The depth is it 10 cm. While the fourth side is somewhat thinner. Oh no. The width is this one. This is width. The depth of the core into the page is a 10 cm. So this is the depth lah. I mean here. This is the depth. And the other dimension are shown in the figure. There is a 200 turns coil wrapped around the left side. So we have an N 200. Assuming the relative permittivity mu R is 2500, how much of flux will be produced by 1 ampere input current? So when we want to solve this question, first of all, we need to translate into something that we can solve. This one we cannot solve because it is not average. It is a 3D. I mean 2D or 3D. By right, it's a 3D because it has a depth. It has the depth here. So the problem is we need to put it in a simple way. So we know that this is source. So plus, minus. We know that because the widths are different, so the L also different. See? So we have R1. We also have a R2. Then the flux going like this. Okay, done. So what we need to do is R equals to L over mu A. So 1, 1, 1, 1. 2, R2 equals to L2 mu, mu R mu not lah A2. So have a look here, mu R mu not. So R1, what is the length of R1? So L usually we take the mean path, which means we take the tengah-tengah sini. Tengah-tengah, and then connect. Okay, so we need to calculate lah, how much. So this is a 30 plus 5 plus 7.5. Right or not? This one is 7.5. This one is 5. Okay? So 30 plus 7.5 plus 5. And then this is how much? This is 30 as well. 30 plus 7.5 plus 7.5. 7.5, this one is a 15 divided by 2, because every we take mean path, average path, mean path. For example, here half of it we take 5 because 10 divided by 2. For example, here half of it we take 15 divided by 2. Okay or not? Can follow or not?
Boleh.
Yeah. So same as well. We have a 30 here. Then we have about 7.5 here. Then we have about 5 here. So plus up together. So this is the L1. Area is the flux flowing the area. So when we cut here, the area is like this, this is the flux flowing. Phi. So this is the area of A1. So area, how to do that? So this is 15, right? 15, and then we times the depth. The depth is 10. This is 10, given by here. So this is the area. So A1 will be 15 times 10. Then mu R is 2500 given. Mu naught is 4 pi to the power minus 7. This is R1. Then we use calculator to calculate, then we get R1. Okay? After that we calculate R2. So R2, same, the length here, 3 pro. Then the length here is 7.5. The length here is 7.5. How can we get 7.5? It's actually 15 divided by 2. Same as well. 15 divided by 2. So we get L1, L2. Mu the same because the material are the same. This is the core. So which is 2,500. Mu naught 4 pi 10 to the power minus 7. A2. So same as well. We cut here. Then we'll see, okay, the flux is flowing like this. So we need to use this times that. So this is how much? 10. Okay? 10, 10 here. Ketebalan dia. And then that also 10. So A2 is 10 times 10. But you need to change to meter, not cm. Then we calculate R2. We have R1, we have R2. What they want? They want flux, right? Phi. So they need to know what is the flux inside. So same as well. Macam tak cukup tempat tulis. Same as well. We take this as a positive direction. We know that this one is positive, this one negative. When the flux flow through the load, this is positive first, then negative. Then the flux flow to the load, positive, negative. Okay. Then default direction like this. Okay. Maybe I change another color. Okay. Default direction like this. Okay. So green will go touch negative first. So negative. Cantik. This one. Negative and I. Then it touch negative first, and then it go, and then it touch positive. So plus 5, 1, R1. Then it go again, touch positive, plus 5, 2, R2. Then it becomes 0, because no more. Okay? N is given, which is 200. I is given, which is 1 ampere. Phi 1 tak tahu. Phi 2 tak tahu. But phi 1 and phi 2 the same. So we use phi only lah. Phi tak tahu. Ataupun phi is the one we need to find. R1 already calculated from here. R2 already calculated from here. So can we find phi or not? Can we?
Yes.
Okay, thank you. So next, the magnetic circuit made of the magnetic circuit made of the rock iron is arranged as shown in figure. The center limb has a cross-sectional area of this one. So center, this one, A center, it has a 8 cm square. I want to ask you, do you have difficulty to change the unit or not? Can I know anybody have the problem how to get 8 centimeter square into 8 meter square? I mean in meter square. Okay, let me teach you. 8 times centi is 1 times 10 to power minus 2. Right or not? Okay, centi is like this. But because it's centimeter square means cm square, which means this must be square. Then I have a meter square. This one. Can see or not? This one is a c square, m square. But we write as a cm square. But when we want to take it out, meter square, we need to do this. So which means it becomes 8 times 10 to power minus 2 square. Okay? Then meter square. So which become 8 times 10 to power minus 4 meter. Boleh paham?
Boleh, boleh.
Okay, thank you so much. So, and each of the side limb has a cross-sectional area of a 5. This one is a side equals to 5 centimeter square. Calculate the ampere turns. Ampere turns is a Ni lah, or we call F. Required to produce a flux of a 1 milliweber. So given the flux is in the center limb. In the center limb. Here. In the center limb, we want to create 1 milliweber. Neglecting the magnetic flux linkage and fringing. If I say no fringing, which means all the flux only flow here. All the flux only flow here. Okay, I'll come first. Somebody come in. Betul. Okay, sorry. So let's continue. In the center limb, neglecting the no fringing means no fringing effect lah. So what we can see is we have 1 reluctant here, 2 reluctant here, 3 reluctant here, 4 reluctant here, which means our circuit it become, where is the source? Macam tak nampak source. Habis dah. Dia tak ada source. Let me see. Where is the source? What they want? Calculate the ampere turns required to produce a flux F in the center limb. So which means this is the source lah. F. Okay. So we need to convert into a magnetic circuit first. We know that this is the R. Then this is got 2 R. Then got 1 source. Then another R. Okay. So let's say lah. This is RFE. Okay, this is another RAD, but we still have a RG because of the gap. Then this is a RAC, sorry, AD. It's flow from A to D. So this one is a RAD as well. Maybe we use right easier. Right is left. So when we have the circuit, then we can use a mesh analysis to solve it. Like this. Okay. So go back to do this question. Go back. So settle for this. Any question before I proceed? Do you have any question? Ataupun it's too easy this topic because you took already. Can I proceed?
Yes,
Yes.
Okay, thank you so much. Quick. Aha. So next topic should be the heating and cooling of electrical machine, which we need to settle by this week. So it will come out in the test. Atau OBE, I don't know yet. I still not yet prepared the question. So the process of energy transfer in the case, let me see how many people. Oh, 41. Okay. Macam semakin kurang student. Kenapa semua takut saya? Okay, heat dissipation. We will talk about heating and cooling of the electrical machine. So usually heating and of a cooling electrical machine is meant for transformer. If you still remember that electromagnetism got two type of machine. I forgot to change the name. This is a last code. I forgot to change it. Later I will change it in electrical machines, okay, electrical machines we have a static. Okay, we have a rotating. We call electrical machine means a device where there's a conversion conversion that involve the principle of electromagnetism. That's called electrical machine. Usually we divide it into two one is static, one is a rotating. Static is transformer. Okay, we have a one coil, two coil. So there's a transformation. The current become flux. Flux flow through the secondary become flux 2. Okay, flux S. Then flux S become I2. There's a changes. For rotating, yes. The flux of the rotor go to the flux of the air gap, and then go to the flux of the stator. Okay, flux of the stator, and then go back to the gap, then go back to the rotor. So there's a electromagnetism conversion. That is a flow only, and then when it's flow through like this, there will be a cutting of the winding. Then from the winding turn into electricity. Okay, so we focus on the heating first. The process of energy transfer in case of the transformer and electromechanical energy conversion. In the case of the rotating electrical machine, involve current in the conductors and the fluxes in the ferromagnetic parts, the I2R losses in the winding and the core losses in the ferromagnetic cores. This is the two main components we have in the electrical machine, especially in the transformer. In addition, losses occur in the tank wall, end plate, and cover on account of leakage flux. The losses appear as a heat, and therefore the temperature of every part of the machine rise above the ambient medium. Medium means bahan, ambient medium, which is normally the surrounding air. So we have modes. One is conduction, one is radiation, one is convection. So the mode of heat dissipation is important in the case for the conduction. In the case of a solid part, conduction means the energy transfer. I mean the heat release is passing through by using a solid material, if not mistaken. Then we have consider 2 points in electric circuit having a potential of this one. I think this is not so important. So we can rewrite the equation for heat flow by conduction between two surfaces separated by a heat conducting medium. So for example, we have a bar, iron bar. Okay, we give a fire here. Then slowly we will feel the heat here. This is a conduction mode. So maybe this is temperature. Then this is temperature 2. So from temperature 1 flow to temperature 2. Divide by the resistance. Okay, then it will be the conductivity. So when we do, we actually mencontohi lah. Kita mencontohi formula ni, then selepas tu kita dapat formula macam ni. Then we can further derive become like this. So the heat dissipated by the conduction in the watt is actually the temperature of two bounding surfaces, and then we see the thermal resistance. Thermal resistance means rintangan haba. Okay, if let's say the thermal resistance is very high, R naught is very high, which means when we heat up 100 degree here, we cannot get 90 degree here because it's too high. It resists. You don't want to let the heat flow through. If let's say the R naught, or we call the thermal resistance, is very low, so we use 100 degree, then we maybe will measure. Sorry, just now this is maybe 220. If let's say for resistance very low, then we might get 100 degree. Okay. So thermal resistance, which means which cause a drop of the 1 degree per watt of the heat flow lah. And then this is the formula you need to memorize. So rho is the thermal resistivity of the material. Sigma is a 1 over alpha, 1 over rho. Length, I think this is L good, not T. Then surface of the medium. So for the heat dissipated for conduction mode, we can use this equation. Overall, like this. Need to memorize. Oh, I think got given in exam. Thermal resistivity. So different material will have a different thermal resistivity. So for air is a 20, and then let's take about copper. 0.0026 ohm per meter. Ohm meter, thermal resistivity ohm meter, which means in the air, if let's say we give 100 degree, it's very difficult to get 100. But in copper, yes, if let's say we take 100, then in the end, the other end, we might get 100 as well. Now because the resistance is very low. So second one is radiation. Radiation, you know lah, it's something like this. This good. Wait, 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 wait. Radiation. For example, the X-ray radiation. We cannot see the ray, but it emits to our eye. Okay. So radiation from a surface depends on temperature and its other characteristics like color or roughness lah. So the Stephen Boltzmann law saying that the total heat dissipated by radiation can be calculated by using this equation. How to get this equation? I don't know. Memorize, So what is N? N is the Boltzmann constant. E is the surface emissivity factor. S is the surface area. T is average temperature, and TA is the ambient air temperature. It can be in Kelvin. It also can be degrees Celsius. Oh no, I think need to be in Kelvin. Sorry, need to be in Kelvin. This equation must be in Kelvin. So emissivity and absorption factor. Oh, let me see. Okay, let me finish this one. Then we rest for 10 minutes. So perfect black emissivity. When the surface is black, okay, the emissivity is 1. So which means emissivity is which one? Emissivity E. So if let's say it is high, then the radiation is very high. Kereta hitam lebih senang dissipate heat daripada kereta putih. For example, white. White is quite near. Emissivity. Aluminium, white, gray. Let's say black is 1. Then white is 0.9. So if let's say we use a white car and black car than the white one, because the emissivity problem, because it's a convection problem. And then, but at the same time, you can see the absorption rate, absorption factor. The absorption factor is high, which means absorb heat very fast, right? So let's say you see the gray one is about 0.75. So maybe the black one is nearly to 1. Which means if let's say we have a car, a white car and a black car, absorb heat faster is black. Release heat faster also black. But the problem is the white absorb is lower. So not so soon. It won't warm up so soon. So usually we won't go to take the black car because it's very hot. Okay, so we stop here. First, we'll come back at after 10 minutes. Maybe 4 o'clock. 4 o'clock we come back. Okay, see you now.